Good morning. It works. Grab the coffee. We're going to get going. Lots to cover. And then you can get to your gardens later. Wow, this is great. This is really great. Everybody ready to go? Okay, good morning. Thank you. Welcome to Wolfeboro Water Summit 3. Thank you for joining us and being lake-minded. Did you get it? We are so pleased that, again, major funding for this event comes from the Wolfeboro Fund and Edward Jones for the third year. Thank you. We thank them and all other sponsors for making these summits possible over the last 3 years. You please note the sponsors here and thank them if you see them. Yes, this is our third summit. How many of you were here for one of the last two? Show of hands. Wow, so I'm preaching to the choir? Maybe I could just skip my words and go right to the good stuff. So I've been charged with giving highlights of the last two summits, so it may be repetitive for some of you, but those of us with memory issues, it might be helpful. Today, we'll start out learning more about cyanobacteria, from the science to what we can all do via our community initiatives and our local lake associations. So our organization, the Wentworth Watershed Association, is focused on protecting and conserving Wentworth and Crescent lakes and lands. That is why you see us focusing on saving land around critical tributaries like Heath Brook this last year. Back in 2017, we realized as an organization the importance of raising the awareness of water quality issues for our entire community. We wanted to share our passion for protecting our spectacular area lakes and make the case to the Wolfeboro community of how critical water quality is to our economy. It has become clear through the first two summits that the other lake associations in Wolfeboro are similarly focused, and they are with us today. In Wolfeboro, we all live in the watersheds of our lakes, Crescent, Mirror, Rust Pond, Sargent's Pond, Wentworth, and Winnipesaukee. Joining forces to raise awareness and create action steps is important to our community and region. After all, New Hampshire DES says that stormwater runoff accounts for 90% of the detrimental phosphorus in our lakes, and that's why the first two summits focused on mitigation of stormwater runoff. How many of you were aware that the water from Wentworth, Crescent, and other lakes flows into and feeds Lake Winnipesaukee? That factor further reinforces what you have made me hear, what you have heard me say over and over again. We are all in this together. In the first summit, we had speakers tell us of the importance of water to our lives and our local existence. Many of us are disciples of Don, that's Don Kretschmer. Don and others brought the subject home by raising our awareness and providing some important information about the impact of stormwater runoff and other intrusions on our fragile water bodies. As he has said to us in the past, there's a reason so many come here from elsewhere to enjoy these lakes around us. It's our water quality. Yet we all have seen changes. We hear of area beach closings, increased milfoil, and back in 2017, we discussed the possibility of cyanobacteria or algae blooms. 2 years ago, we began asking, why is this happening? What can we do? In response to what we learned from you in Summit number 1, last year we decided to add a special session for landscaping professionals and homeowners called Landscaping in the Watershed, with speakers from New Hampshire DES. From this and the summit last year, 10 homeowners signed up to be visited and received advice on mitigating stormwater runoff on their properties. Along with those 10 visits, a demonstration site was selected, and a team from New Hampshire Soak Up the Rain and Wentworth Watershed Association members got down and dirty and installed an infiltration step. I'm pleased to say the homeowner reports that the step works well, and the water that was directly running into the lake has been stopped. Every effort like this helps. We urge you to visit the Soak Up the Rain table, and Dan Ross has photographs over there by the back of the room. He will provide information. He will help you sign up for assistance on your property. You'll learn about applied solutions like beautiful rain gardens, pervious pavers, infiltration structures, stabilized ditches, native planting on water's edge, protection of wetlands, best practices for road maintenance, and all sorts of other ideas to take home. So we have all witnessed the increase in severe storms and flooding. We may be seeing new erosion and signs of stormwater running off our land. The stormwater picks up and carries the nutrient phosphorus and also carries metals, bacteria, oil and grease, road salt, and soil. The ultimate recipient of this runoff is our precious waters. Watersheds literally shed their water as precipitation collectors into downstream bodies of water. That is why we must conserve our connected watersheds so they can effectively do their jobs of infiltrating. Specifically, in the last summit, number 2, we showed progress on reducing stormwater runoff and how we can attack this culprit. As examples of solutions, we had experts detail stormwater engineering and infiltration techniques. Those currently installed by the town are supported by New Hampshire DES 319 grants in partnership with volunteer efforts and private funds from the Wentworth Watershed Association. It's only the tip of the iceberg of possibilities, and we hope to see more installations. We can all pitch in with efforts and funding. Unfortunately, last summer, there was a reported cyanobacteria bloom in Winter Harbor on Lake Winnipesaukee. Consequently, this summit number 3 is focused on cyanobacteria and has brought all the Wolfeboro Lake associations working more closely together to plan and deploy resources and share information on a coordinated basis. The town Cyanobacteria Committee has been formed recently. You may also be aware that Wolfeboro is in the midst of town master planning. Also, the continuation of the Winnipesaukee Watershed Management Plan is now reaching the Wolfeboro area. These initiatives will bring added focus and coordination to protect our water quality. Community teams will form beginning today. Volunteers like you are needed for testing, monitoring, and sharing all kinds of data, even visual observations, and we hope you will join in and help. There are all sorts of ways to join the effort, and we'll explain more this morning. So next year, Summit 4 will be on May 9th, 2020, and hope to see all of you here with bringing 3 or 4 friends. We look forward to reporting back on additional community successes and water quality progress from this growing momentum and concern around stormwater runoff and cyanobacteria. As we proceed in all aspects of this program today, please write your questions on these cards, and there are more up here, and raise your hand if you need them, as well as program feedback for Summit 4, because we really use that to plan for next year. Don will moderate questions. Check out the tables at the break, as well as the food. Each lake association has a sign-up and a representative. Every positive effort adds up. So without further delay, before I get into this, I want to say Jim Haney really inspired us to do the Water Summit. We heard him speak probably 5 years ago, and I said, we got to get ahead of this, or we've got to be aware, we've got to know what's coming. So without further delay, I draw your attention to the impressive biography of Dr. Jim Haney of UNH. I have heard him speak a number of times, and it is truly unforgettable. He has warned us of blooms and the consequences, so we are pleased to have him with us today to inform us. Please join me in welcoming Dr. Jim Haney.
Let me just see if this comes off. Yes. Oh, good. I'm not very good at standing still, so this will also add important steps to my Fitbit. So, first of all, I want to thank Anne and Julie, who I've communicated with on inviting me here to this summit, this most impressive venue that you have. But most of all, I think we talk a lot about the importance of citizen science at the university, teaching that for many of our problems, it's just like your house. And incidentally, ecology is the Greek word for house, oikos. And you wouldn't think of having someone else come in and take care of your house, but when we talk about lakes and their ecology, it's really our responsibility to make sure that they're being taken care of. And I think you're going to see some of the relevance of that to not only the lake, but to your own health, as for example. So I'd like to thank everyone for inviting me here. It's quite an honor to be in such a energetic, enthusiastic audience, and also just the intentions of this are so good. So with that, I'd like to just introduce the talk that I'm going to give, which is on the ecology of cyanobacteria and problems of cyanobacteria in lakes. I've sort of put here, why us? In other words, it's always a good question is this something that we've done that's causing it? And then why at this particular time are we so concerned? I was also, I think it may have been Anne, I'm not sure who asked me not to scare you too much. And that was Julie, so you can thank her. But it probably won't have much of an effect upon my talk. I'm sorry, Julie. What I really want to just simply open you up to is what the state of research on cyanobacteria is, what they are, and not so much in terms of scaring you, but to make a realization of what sort of a threat this may pose and why it's important to do this now and not put it off for another decade or two. So, this is sort of the first part is kind of the ABCs of cyanobacteria. Is this too loud or too soft? Okay, that's good. I'm not used to using these, incidentally. I just sort of yell. Okay. So let's go through just so you have some idea of the background. Until about the 1970s, they were called blue-green algae. It turns out, as I'll mention to you, technically that's not correct. It's worse than if you were to identify a whale as a fish, but it also is understandable because it's part of our language. So the reason for that, just in case you're interested, is that in the marine systems where toxic species were first noted, they were in fact algae. And so these were called harmful algal blooms. That's correct. But for freshwater, most of the blooms that we see that have toxins associated are cyanobacteria. So we call those HCBs. So if you want to be technically correct, that's where I would suggest you sort of work on that. So this simply is a little lesson from the tree of life. And if we look at where we are, we're called the eukaryotes because we have cell membranes and a nucleus in our cells and produce all sorts of fancy things like legs and nervous systems and all that. But the algae actually share that with us. The cyanobacteria are way over here, and they're what we think of as simpler, but in many respects, they're not. They're just small. And you're going to see that some of the reasons we have problems with them is that they've been doing this for a long time, and their focus is not so much on structure becoming big, but on chemistry. And they're the world's best chemists, I would argue. So, these are just some points. If the cyanobacteria actually were, in fact, amongst the first organisms on Earth. Very quickly, organisms, the biggest problem they had is running the machinery. That is, how do they keep what quantum physicists will call a thermodynamic disequilibrium. That means that energy has to come in, energy has to go out, where do they get the energy to sustain life? And of course, it was the sun. So the first bacteria that were using the sun were cyanobacteria. And they, of course, inhabited all these lakes and oceans and everything before there was any inkling that there would be larger forms such as us. In fact, one of the things that we have to think about then is get away from the idea that cyanobacteria have invaded our lakes, because they were there long before people were around. So the question is, how do we live with them? How do we get along with them? How do we keep them at levels where they don't present a problem? So if you look at blooms, what we talk about is harmful cyanobacteria blooms. They can be as simple as this. This was simply out on the campus. This is oscillatory or planktothrix, just a little strand of this out there. That strand, however, could be very, very toxic, even though it's small. And then you go over to other extremes, such as the St. Lucie River in Florida 2 years ago, actually last year as well. And then as big as hundreds of square miles of cyanobacteria in Lake Erie. So these blooms can be very different, and they can be very local or they can be very general. So one of the problems is, how do we anticipate that we're going to have a bloom problem? And if we do a management, how do we actually evaluate that we've had an effect? So do they happen by design or by accident? And this is simply to remind us that what we're dealing with here is not a toxin that we've tossed into the water, but an organism that lives there. And in that sense, they have evolved there. So if we're going to manage them and live with them, we have to understand their ecology, because they're part of the system. So just when you think about that, keep that in mind. I'd like to just then sort of put the context here for what we're going to be talking about is what is their evolutionary context, and then talk about, first of all, what we call the bloom-forming cyanobacteria, or BFCs. These are the ones that we see the scum, and they tend to be, relative to other cyanobacteria, the big ones. If you put them, you won't see them individually unless you put them under a microscope, but they're actually quite large, and sometimes the filaments themselves are, of course, macroscopic. So one of the things that's interesting is, with climate change, cyanobacteria, and there was this article written in Science in 2008 by Hans Perl, a well-known cyanobacteria researcher, and he called it, the title of the article was "Blooms Like It Hot." And so his idea was that cyanobacteria will dominate when you have nutrients that are at high levels, especially phosphorus, but also nitrogen contributes to that. Not all cyanobacteria can produce their own nitrogen. And then if you have warm temperatures, they grow best in the warmest summers. In our lab, we have to have special aquaria that, if we're raising them, that are just about a degree or two above what other species of phytoplankton can tolerate. That's where they do best. Then thermocline stability. Most of you probably have some awareness of how in the summertime you have then the mixing layer at the surface, and then you have a cold layer at the bottom, and in between what we call the thermocline, this rapid change in temperature. The thing is that the bottom water never mixes during the summer. And it feels cold not because springs are coming up, it's because that was the water that you have right now, and it stays there. So cyanobacteria can use that as a refuge. So we're going to see why. And this is the reason why, is that they actually have very low light requirements. So they can live where most of the other good phytoplankton, we can think of them, can't live. And so they do well at the bottom of lakes, but also whenever lakes become turbid and bloom, they're actually shading themselves, but the cyanobacteria do well under those conditions. So this is what we want to avoid if we want to control then the abundance of cyanobacteria. So when are they present in the lake? Well, let me just show you the general pattern that we'd see of phytoplankton in lakes. And in the springtime, which is now, we're going through a period when the really tiniest of really microscopic but almost submicroscopic pico and nano phytoplankton comes up. Diatoms tend to be dominant here. And what happens is that will pass. So we usually get a period of kind of high turbidities in the lake. You go out and it doesn't look as clear as it will later on. That's because these forms here grow really early, and then they actually give rise to the second ones, which are the greens and goldens, typical of many of our oligotrophic lakes. And then late to midsummer to late summer and into the fall is the period when the cyanobacteria come. So if you're going out there now, it's kind of hard to judge what it's going to be like in the fall, because there's a whole sequence of species. And this Clearwater phase is really interesting because it actually can go then from maybe a meter or two secundus down to 8 to 10 meters within a week or so. Very quickly then it clears up, and that actually is caused by abiotic interactions. So this is just a quick, go through this very quickly. This is simply to show you the annual cycle here of the cyanobacteria in the lake. So in the winter, a lot of the cyanobacteria can be on the bottom of a lake. In the springtime, with increase in temperature and light, they begin coming up in the column, and they sort of, that's where they are now. A lot of these are picoplankton, which are cyanobacteria. And then the zooplankton, which are the crustaceans in the lake that graze on these, they become dominant, and they actually cause this spring clear water phase that I was just talking about. And then as the temperature increases, you get more growth. So now we're talking about May, June. And this is about the time when these deep layers start. So this deep layer here can form either from cyanobacteria coming from the bottom, or actually just cyanobacteria aggregating where they have the best light and the best nutrient conditions, because there's lots of nutrients in the bottom of a lake, and so they tend to push down as far as they can. So this is what we call a subsurface bloom. So that one you wouldn't see even if it was occurring, but it's in a lake. And then you get sunny and calm weather, and you have thermal stability, so you get these bands and such. And then what happens is the cyanobacteria tend to float up. And when they do that, they actually can aggregate. And this is why we get enormous quantities of cyanobacteria, not from just that location, but they actually will aggregate in a cove or an embayment, and it may not even be the embayment that's producing them. In Lake Champlain, a very large, long lake, in the northern section of Lake Champlain, they get enormous densities of toxic cyanobacteria coming from the lower part of the lake in part because of the winds. So this can then, we've estimated, concentrate somewhere from 1,000 to 50,000 times, if you do the math on this, over what the lake level is. So this is when you get these surface blooms that can be highly toxic, where in fact something as small as a teaspoon or a half a teaspoon would be enough to kill a dog or small child. So that's whenever it becomes very dangerous to use the water in any way. So what's the climate impact? Well, if you look at across the United States now, in the last 100 years, we increased the temperatures about 1.8 degrees Fahrenheit. But in just the last 30, we're now up to 1.4, and this is changing as we speak, so to speak. So the whole United States is getting warmer, which is moving us toward the conditions where the cyanobacteria do best. And so the model predictions are that we're going to have sort of a 4 to 9 degree Fahrenheit increase in the minimum winter temperature, which definitely could have a big impact. And more precipitation, which means more runoff. Hey, things couldn't get better, right, if you're a cyanobacteria. So, so what it's going to mean is New Hampshire is actually, the climate that we have now is actually going to look pretty much like we would expect down in Virginia or North Carolina. So that's the future with the way things are predicted. We're thinking about it primarily from the standpoint of cyanobacteria, but of course our whole natural setting is going to change. We're going to find that the salmonids are going to be going north, because to find them we need to have cold water, especially things such as lake trout and brown trout. So in other words, this environment is changing, not just the cyanobacteria, and part of that we have to cope with. We can deal with wildlife better than we can deal with the changing environment for cyanobacteria, because they're going to be increasing, according to all this. Okay, this is just, I took this out of the talk last night, but let me just show you what I was taking out of the talk last night. I won't put it in there, okay? So the interesting thing is that people have modeled when the phytoplankton bloom, phytoplankton meaning cyanobacteria included, and looked at the effect using hundreds of lakes to model what's going to happen when we change the temperature. And basically, this is this clear water phase here in the normal temperature. This is this dip, and then it goes up and you get the blooms after that. But what happens if you, in fact, increase the temperature? You find that, in fact, you are putting ahead the time of the clear water phase, which means there's a longer period when the phytoplankton can bloom. And so the bottom line is that for simply a 1 degree temperature change, that's Celsius, you would get a shift about 7 up to almost a week then earlier that you're going to get blooms. So this is simply to show you that you can model that there is predictable, at least a model prediction, of increasing length of period when blooms are going to be a problem. Okay, so how much do we need to know to manage? This is where my interest in cyanobacteria began, actually. I was invited to participate in a workshop which extended into a sabbatic in New Zealand, because in New Zealand, blooms can go on for months, but they can also go on for years in some lakes. They just, because the temperature allows for this, and many of the lakes we worked on looked just like this. One of the things around here, we don't usually get blooms occurring like that, but actually what happens is the blooms are there one day or not there one day, and then the next day you go out and suddenly you've got this stuff. So where does it come from? I tried to illustrate how this happens with some water I brought in from Massachusetts, illegally probably, Quantapowhat water. And we just collected some water in this lake that had lots of cyanobacteria in it, and put it into a bottle and said, what happens when you bring this into the lake, or bring this into the lab and watch it? And so I did that, and you can see the direction of all these cells going up. They're collecting at the surface. This is just done with an iPhone, so there's no, it's normal trickery here, I would say. So basically, they go up to the surface and collect because they have buoyancy. And this illustrates it very well, that it just, within no time, you've got this collection of a bloom at the surface. So when you go out to a lake, you don't see anything. It could be because they're on the bottom or in the deep water, and then they move up. So one of the problems with blooms is that they don't contribute to the growth of other organisms in the lake, and especially things like fish. This is a Daphnia here. Oh, I'm sorry, this has got the sound turned on. This was in our lab, and we always get very excited when we see things, so ignore that. But basically, what it's showing is these big filaments coming in are cyanobacteria, and so it kicks them out. This Daphnia here takes them in, filters them in, but then it rejects them. So they're really not helping the system in terms of productivity. And in fact, in some cases, they are toxic to these grazers. So we've designed a food web that incorporates this idea that the big organisms we see at the surface, we call the BFCs, they're bloom-forming cyanobacteria, they don't really contribute to the growth of fish and other wildlife in the system because they're inedible largely. But it's these guys here which are so small that you have to put them under special fluorescence to see the individual cells. So this is the world of cyanobacteria isn't as simple as we think it is. It's not just the blooms. There's lots of other cyanobacteria there. So these are the edibles. They can also be toxic. So they're feeding toxins into the wildlife, and these are creating surface problems for toxins as well. So if you look at this as a model, these are the big bloom-forming cyanobacteria. They grow slowly, and they transfer toxins slowly, except when we recreate. And then they move up to the surface waters and eventually cause the blooms. And in the wintertime, what's left of them will come back down into the sediments. This is the other side, which is the really tiny things, and they actually feed into the food web and become part of the food web, which leads into the fish and ultimately into higher levels. So you've got then cyanobacteria doing different things. So as you might suspect, it's not a simple system. They designed it long before even algae were present. Okay, so after a bloom dies, we often wonder what happens to a bloom. And one of the things we've been doing in the lab is putting different types of bloom-forming cyanobacteria under conditions where we would give them a dark shock. In other words, if they settle out, what happens to them? What we find is within a couple of days, the whole colony breaks up, and now it's available to go into the food web. So we didn't understand that. So when they're blooming, they're not contributing to the food web, but later we think they may be. And as a result, then toxins can enter the food web from them, but only after the bloom has disappeared. So you say, well, the bloom's gone, okay, everything's good, but actually that's whenever these toxins can be having their effect. So, so where are the toxins then? In surface blooms, as this Hans Perl photo shows, that in fact in China they have real serious problems, but not only in China. This is a summary done by Cadella. He looked at some of the worst lakes in California, and these are some of the microcystin levels, keeping in mind that microcystin, the recommended by the World Health Association, is 1 microgram per liter for drinking water. Here's the levels he was finding in some of this. 5,000 in the lake itself, in the scum, 95,000. Pinto Lake had then 1,000 micrograms per liter, 1,000 times the drinking water standard, and 2.9 million times the drinking water standard in the scum. So all that means is it can get pretty bad. That's the point of this slide. Of course, it happens here at home, and this is one of many, many cases of dogs where having consumed water that had cyanobacteria in it, and some of it can be lethal within hours. So that's, and especially when it's concentrated like this. So if you see a dog or you see people recreating with this condition, you should really recommend they don't do that in case they're not aware. So the toxins actually that are in the cyanobacteria, these are two of the ones we're looking at, a liver toxin, which is microcystins, and then a neurotoxin, which is BMAA. And we're trying to better understand how they move through the food web and what effect they have on organisms and on people. So these blooms then have, because of these toxins, created then a need to put signage up that warns people of their presence. And we see, this is York Pond up in Milan, New Hampshire, and we get die-offs of fish sometimes in there simply because there's so much cyanobacteria there coming from a fish hatchery. Sorry, shouldn't say that. So this is right in the middle of Dover, New Hampshire, and this is Willand Pond, and we get some spectacular blooms there occurring, although they've had some great success in reducing the frequency of this by controlling the nutrients. So there's a great example there. This is Lake Erie, of course, where parts of the lake then have such high levels that you can't drink the water, of course. And the other thing is that the cyanobacteria can get very, very dense, not only on the surface, but below the lake surface, as I mentioned. And I just thought I'd show you a picture of Mirror Lake here, in which we went out with a class and did a profile of chlorophyll, which is this green layer here. This is going down here to the bottom. This is the bottom of the lake here. And then the blue-green line here is the cyanobacteria. So if you look at the cyanobacteria level in that, it was at around 8 meters, and it was very, very dense. And you can see that it was a very thin layer. So the question comes up is, well, is that a threat in itself? And we had a good fortune of having Sabina Perkins, a graduate student at UNH, has been looking at that this past 2 years. And in fact, she's done some work on Mirror Lake. And she should be finished with her thesis in a month or two. And Bob Craycraft here can probably point you at the direction if you want to see the results of this. But one of the interesting things is the 3 lakes that she looked at did not have high levels of toxins in them that we saw, at least the microcystins, which is encouraging. So, because these could represent a real threat, but we need to expand that study now to see if that's true for other lakes. So, if we look at the accumulation in the food web, one of the things we've been looking at is loons and how the toxins feed into what we call the apex predators, that is the top level carnivores, and we have loons, of course, in Winnipesaukee as well. Some places have eagles, which could take it a step higher. And one of the questions we have is whether these toxins actually end up in the birds at the top, coming from the phytoplankton below. So we're asking this question. And we did find some interesting evidence by taking blood samples of loons that we found a correlation of this neurotoxin, BMAA, with the amount at the bottom level, the phytoplankton and zooplankton, actually was correlated with the amount we found in the blood of the loons, looking at about 30-plus lakes in the northeast and in the west as well. So in other words, this toxin being produced is working itself up the food web. The question of what harm it's creating for these organisms is yet to be determined. So just a quick note on public health here, because obviously that's something we're also interested in. And one of the first connections I had with it is I had a phone call from Dartmouth-Hitchcock Medical Center, and a person that at that time I didn't know, Elijah Stommel, a physician there and also a PhD, called me up and said, you know, we're getting clusters of ALS patients around certain lakes, and especially around Lake Mascoma. Is there anything happening there? And in fact, this says that there was 25 times the expected incidence of ALS. It turns out this is closer now to 70 to 80 times. And so the question was, what is it related to anything in the lake? So we began sampling out there and did find BMAA in the lake. No proof that that's causing this, but it started us looking at water quality and human health. There was coincidentally, and this is 2015, a study done across the U.S. of water quality and the incidence of non-alcoholic liver disease. And what this researcher, Zhang, and his co-authors found is, in fact, there was a significant correlation between the incidence of liver disease and the water quality in lakes throughout the U.S. And that, again, is just a correlation. It could be connected to something else, but it's enough to cause us to want to know more. A similar study on a smaller scale was done in New England, in New Hampshire, Vermont, and Maine. And the question being asked, this was done by Nate Torbick, who some of you would know here, who is also a graduate of UNH. He looked at the risk belonging to a cluster of ALS associated with water quality and especially with cyanobacteria presence. And when he did this spatial analysis, what he found is that In fact, if you increase the water clarity by 1 meter, within a radius of 30 kilometers of the water bottle, you decrease the odds of belonging to a cluster of ALS patients by 59%. It's a statistic. And you did this for nitrogen and chlorophyll as well. It's a different way of looking at it. What's the odds of becoming a statistic yourself, belonging to a cluster? So what it said is that water quality statistically is correlated with the likelihood of being part of a cluster of ALS patients. Again, it doesn't prove that there's a direct connection, but it's enough to know that it's worrisome. So we asked the question, how are the cyanotoxins getting into people then? If it's within 30 kilometers of a water body, it doesn't necessarily mean people were drinking the water. They certainly probably weren't in most cases. On some they could. They may or may not have been recreating. But one thing we do know that they were doing is they were breathing. People do that regularly when they're alive. So the idea is, so what we've done is we've developed a system for measuring what we call the lake-generated aerosols. Now, if you go to a dam like this dam here is about a half mile from my house, so I walk there most evenings, and I took a picture of what it looked like. And so you can see the aerosol being generated by water turbulence. And this is coming out of the Milton Dam. And they happen to have a light there, so you can see this every evening, all this liquid aerosols. What we discovered, which was really interesting, is you don't need to have a dam. In fact, if you put these aerosol collectors out on a quiet lake like this one here, this is Kate Langley's master's thesis. She'll be done in about a month or two. And these were what we call non-wind generated aerosols that just like you open a perfume bottle and you don't need wind to smell the perfume, right? It's coming out of the bottle. Well, toxins and in some cases really small cells come out of the lake water. Big surprise. We make a disconnect between what we smell and what we see, and we say if we can't see it, it's not there. But we know it's there, these molecules. So we have begun studying then this type of aerosol because it's everywhere, and it depends on what's in the water then. So the toxins come out of the water, and in some cases, the small cells. Paul Cox began a study in 2003, and he's become a colleague of mine, and he discovered at that time that in Guam, where they had 100 times the level of ALS, again, a cluster in that whole island, but just in the indigenous people, the Chamorro tribe. And what he discovered is that the Chamorro tribe was actually getting a toxin, BMAA, from a cyanobacteria that lived in a tree that produced the fruit that a bat ate, and they ate the bat. So it's kind of like this food chain. And I don't have time to go into that now, but it's a really interesting story because that explained why such a high incidence of what they described as ALS, Alzheimer's, and Parkinson's symptoms. So it was neurological. And so that started Paul Cox on a trail, and he now runs in Jackson, Wyoming, what he calls the Brain Chemistry Institute. And that's where they study this stuff. In fact, I just wrote him the other day because we have a paper coming out on some work we did in Boston on the Charles River, showing the toxins are coming out of the Charles River, and he accepted that for publication in a journal called Neurotoxicity. So, this is ongoing stuff. So what happened then is that in Guam then they found that not only was it in the bats, but it was in the brains and nervous system of the Chamorros. But then at the University of Miami, they also discovered that if you looked at the brains of people who had died from Alzheimer's or ALS versus died at this similar age of other diseases, that almost entirely, but there were a few exceptions, the ones that had BMAA were those who had the neurological disorder. So we know they weren't eating bats, probably. So the question then is, where are they getting this neurotoxin that's produced by cyanobacteria? So that got us back to the lake, okay? So the model that, and this is sort of interesting to take it to the next level. So how does that work? Why does BMA cause a disease such as either Alzheimer's or ALS? And one of the interesting work done by Deborah Nash in Miami is that she claims that BMAA is a really tiny amino acid that gets mistaken for a good amino acid. And here's how it works. If you look at L-serine, which is an essential amino acid, you can buy it at the health food store. And if you look at BMAA, the molecules are almost identical. And to the body, whenever they're putting together proteins, they're designed, the genetics is designed to pick up L-serine, but if there's lots of BMAA around, it mistakes the BMAA for L-serine. When it does that, it will, here's a normal folded protein, and here's the L-serine. If you put a BMAA in here, it doesn't fold the same way. And this is why sometimes Alzheimer's is referred to as a tangle disease, because proteins then are misfolded. So the idea behind that is that Cox had is, what if we add more L-serine to our diet and dilute out the effects of BMAA? And what he's discovered, first of all, with vervet monkeys, and this came out about 2 years ago, this research, that if they fed vervet monkeys BMAA, within 140 days they developed histological symptoms of Alzheimer's. But whenever they gave the monkeys the BMAA plus the L-serine, they didn't see that development of the misfolding. So it sort of confirmed that this model might have some validity. So now I just wanted to show you where this is. This is the timeline on BMAA, and if you take it to where it is now, they got approval to test out on humans the effect of L-serine, and now in 2017, over at the Dartmouth-Hitchcock Medical Center, they're now doing these tests of people giving them L-serine or not, and looking at whether or not this is having a significant effect. All this is simply to say, we don't know whether BMAA, if it's found in a lake, is causing this, but we're trying to move toward understanding it better. And this is why the science is so necessary, but also the work of citizens in getting information that we can use to back up this science. So this is where we are now. We're right at trying to figure out this puzzle. And one of the ways then is through citizen science and partnershiping. This is work we're doing down in the Cape in Massachusetts, and it's very, very exciting because they're almost as energetic as you are. And this is what it has to, where it comes from. And so they have organized, the first year we were down there, they did, I think, 13 lakes. Then last year, they're up to 35 lakes, and now we're going to be doing over 100 this year. And they're doing monitoring for cyanobacteria and also monitoring aerosols. They became interested enough in it that they asked us, could they purchase some of these aerosol collectors and also pay for the analysis? And the town did that, the town of Brewster in Massachusetts. So it's simply, to me, it's further proof that citizen science can go very, very rapidly when sometimes science in general is very slow. So I'm just about at the end of this. Am I at the end? Oh, I've got lots of time then. Let me tell you another story that sorry. But what I wanted to point out, because this is the next step, and hopefully we'll have a chance to come up here to do a workshop on the actual monitoring, but I wanted to point out one of the things about cyanobacteria that is an advantage to them because of their light requirements, but is an advantage to us because now we can find them, is the fact that they have 3 sets of pigments. Most phytoplankton have chlorophyll, and sometimes different types of chlorophyll, but this is the chlorophyll here. And if we want to find those, we use a blue light that's absorbed in by the chlorophyll, and then that tells us how much chlorophyll is there. They also have a phycoerythrin, which is a red pigment, and they also have a blue pigment here. So they have at least 3 different sets of pigments and some in-between pigments. But these are the 3 major pigments. What that means is they can collect light in wavelengths that other phytoplankton can't. So if they go down deep in the lake, just keep in mind, I don't know if you've ever done scuba diving or even snorkeling. If you go down very far, you lose all the color. It becomes pretty much blue. And so when a phytoplankton is down there, it's not interested in seeing things, but it needs that energy. So what this says is that these cyanobacteria have the ability to pull energy out of the light in different wavelengths. Now, how are we using this? Well, what we're doing then is with laser beams, you essentially then have a laser beam that's blue for chlorophyll, one that's green for phycoerythrin, yellow-green actually, and then one that's sort of orange for phycocyanin. They absorb those. When they absorb that light, they flash a light out that we can measure. So that's fluorescence. And so what we found is that, in fact, if you look at the amount of fluorescence in the blue pigment and correlate that with the amount of toxin in the water, what you get is interesting. At first we thought it was a lot of scatter. And then when we started saying, well, the scatter down here is in those lakes that have what we called Anabina, Dolichospermum here. And then the ones way up here at the other end of this were actually all those that had Microcystis, another species of cyanobacteria. When we parsed those out, we said, wow, there are really 3 different curves here. And so if we want to predict how much toxins in the water from the amount of pigment, we can do it only if we identify what's there. Well, why don't we identify what's there? So now we're having citizens actually do what we call the 100 count, and they count what type of cyanobacteria are present in their system. And with that, then, it gives us a much better resolution on using that pigment as a way of saying, is the toxin now at a dangerous level? Well, why don't you just send it in and have it measured? Well, the problem is it's money, but also time. If you want feedback, you need to have it like today. If you've got a bloom in front of your house and you want to say, how toxic is that? You don't want to read a report in the fall about the toxins. And unfortunately, that's just the nature of the way it works. So what we're looking at is using then this fluorescence as a rapid feedback so that you can actually be sort of in control in the sense that you see something, you can measure it, and with a little assistance, you can interpret then what it means. So what we're doing then is, and what we'll be showing you, hopefully, if Hillary Snook comes up with the EPA and brings up his show, and I hope to be part of that, we'll be actually demonstrating how we can then isolate the bloom-forming cyanobacteria so we can identify them with a microscope and then use online keys to identify those, all made simple with the idea that you don't need to know everything. You just need to know something, the right things about cyanobacteria. So, and these are some of the fluorometers. We just had one redone, so we have included this red pigment that no one else has used yet. But we think that having these 3 pigments and then also ratios of these pigments will allow us to further hone in on what toxins are present. And we're going to be updoing our website, and the idea is we're going to have then, hopefully at some point, maybe this summer, what we call Cyanocast, which is taking this type of data and allowing you to actually make the predictions. You can say, well, we're this close to the World Health Organization or the states or the federal limits for microcystins. That's power to me. And then you can, maybe your local health officer can decide whether you need to put a sign up, You don't have to go through one agency on that. And because the agencies just are overworked as it is. I mean, it's not working, and this is a possible solution. So that's why I'm excited about it. So that's what I want to thank a lot of people associated, and some that are not up here. Bob Craycraft in the front row. Aren't you proud, Bob, that I put this up here? And a lot of other people that have been involved in our work. It would take many more. I said here, many energetic and talented undergraduate researchers. Our lab has maybe 25 to 30 undergraduates per year working on cyanobacteria problems, almost solely. Bob has, and another core group working on the lakes monitoring program. So there's a lot going on, but it won't work without your help as well. So, not yet. Okay. Yeah, you're very welcome. Just here, forward and back. It's on. Thanks. Now I'll have to bring this down.
We now bring you Dr. Muir, but if you have questions for the first three speakers, please write them down so that we can address them right before the break. This is Dr. Warren Muir, who's talking about what we're going to be doing locally. Shouldn't wave this up. Oh, question cards. Can you guys hold up your question cards so we can see that you have them? If you need them, we'll pick them up. We've got question runners who will come around and collect them from you or give them to you.
Well, we have a good turnout. It's great. I've summered here in Wolfeboro since 1950, and lived in summers in our family cottage since 1953, and have been living here year round for about the last 7 years. And I can tell you that when I was young, we really enjoyed the lake, and we by the house, the sand. We had sandy beach. We had sand out several feet deep. The sand was very clear, and then there were a few rocks that were further out, and we'd love to swim out there and stand on the rocks as young folks. But over the decades, I and then my children started to witness that there was more and more growth on the bottom of the lake, and that the rocks were slippery to stand on because they were being coated with growth, and so clearly the quality of the lake was deteriorating over the time, and we've been observing in recent years a continuation of this, and algae, for example, and growth on the bottom of the lake. And this was just this past September, right by our beach in Winter Harbor. And then again in shallow water near our house. So we've been seeing more and more of this type of growth, and it's more observed and in greater concentrations as the summer goes on. Now, and we express concerns because we knew that that the deterioration of the lake undoubtedly was associated with an increase of nutrients flowing into the lake. And we were also observing a number of sources of storm runoff into the lake that weren't present when I was young. And so started to talk to the town, particularly for those sources that town culverts and so forth were associated with. And then this past summer, we at the end of August had a bloom of an unusual type of cyanobacteria called Gliotrichia, and this was collected off of our dock in Winter Harbor. And each of those dots, which you can readily see, is a colony of about 5,000 cyanobacteria cells. And so we had a pretty good concentration of it, and that concentration increased over about a week, so that the surface of the water, just looking at it, had a whole bunch of clumps of the cyanobacteria, those dots aggregated, and looked like that. And so, needless to say, we were dealing with more than green growth on the bottom of the lake and slippery rocks. In fact, the concentrations were sufficient that New Hampshire Department of Environmental Services issued an advisory at the end of August that lasted lasted past Labor Day and well into September, advising people to avoid contact themselves and their pets with the lake. And so it just raised a whole different specter of concerns, but more importantly, it underscored the need for us to be able to get on top of the nutrients that are flowing into the lake that are one of the important controlling factors here. We don't control the temperature of the lake in the summer, but we do have much more control over added nutrients to our water bodies. Now, I was asked to speak to the town selectmen at their next board meeting here in Wolfeboro, and I showed them these slides and a couple of more, and they expressed a concern over this, and I'm very happy to say that as a result of that, the leadership in the town and the department heads in the town have organized a cyanobacteria task force to try and address these problems and try to do what we can to assess the conditions, to prevent future blooms, to mitigate runoff in the lake, into the lakes, and to communicate effectively to the community and all interested folks. And so, really, a lot has happened in the last year, and I'm very happy that there are a lot of efforts now to try and deal with our water quality, which is threatened. But I don't want concern over the threat to go too far. We found out, for example, around Thanksgiving time, because that was when we could get the cyanotoxin analysis back, that there was no significant amount of toxin associated with that bloom. And so that's great. We also have been collecting, I've participated in the water sampling program that Bob Craycraft, who will be following me, will be talking about at UNH. Collecting samples at several different locations in Winter Harbor over the last 3 years, and processing them, providing them to UNH, where they carry out the analyses, and then later give us a report back on what they found. One of the things we found is that the water quality, by those measures in Winter Harbor, is actually pretty good, and is better than the average lake in New Hampshire. And so we're with a situation where, by those measures, the water quality is very good. On the other hand, we experienced a cyanobacteria bloom, a gliotrichia bloom. And one of the things we've been able to learn as a result of these results is that in many respects, gliotrichia is different than many of the other cyanobacteria in that this cyanobacteria spends most of its life in the sediments and is getting most of its nutrients, at least the phosphorus and so forth, from the sediments rather than the phosphorus in the water. And it has the ability to float to the surface and produce its own nitrogen and go through its life cycle, and will do so for a short period of time. Gliotrichia, I think Dr. Haney's lab and others have shown that there are toxins associated with gliotrichia, and so the fact that we didn't have dangerous levels last year doesn't mean that a future bloom of this cyanobacteria will not. So the town has organized a cyanobacteria task force as a result of this to assess, and the mission statement is this: to help coordinate a community-wide effort to assess the conditions of our lakes, to identify sources of nutrients, to identify actions that we can take to identify the status of our water bodies, to mitigate sources that we can of runoff and of nutrients into the lake, and to take actions to prevent future runoff, and to communicate to the community and to all affected interests, to landscapers, shoreline owners, to all of us. If you live in the watershed, you are involved in this. If you live in the watershed, there are things that you can do to try and help deal with these threats. If you live on the shoreline, you have some special opportunities to contribute to the control of these problems. If you're one of the people who still drink water directly from the lake, it's important for you to be well plugged into this, because you don't want to be drinking cyanobacteria, and you certainly don't want to be drinking the water when there are significant levels of toxin in it. So the town has this cyanobacteria task force. It started in December. It's met monthly. It's got subcommittees associated with these functions. And the fourth function of which is to create a protocol to make sure that the communications people know who to notify and how all the important folks who are potentially affected or who can respond to the situation are informed appropriately, so that if beaches are affected by a warning, that Parks and Recreation are aware of it and can properly post, for example. All right. I want to emphasize again that there are plenty of opportunities for you to be involved in this. And during the break and after the panel discussion, which will focus specifically on actions that we can take, there's an opportunity for you to sign up. And the best way to do is to sign up with the Lake Association which you're most affiliated with, and if you're not particularly associated with Winnipesaukee, Crescent Lake, Wentworth, Sergeant's Pond, Russ Pond, or Mirror Lake, go to the Winnipesaukee desk where Pat Tarpey and I'll be there, and we'll get you plugged in. But there are volunteer opportunities in a wide range for people to be involved. We're looking for people who can participate in the collection of water samples in locations where we have a limited amount of data or no data, and there are a number of spots, including Wolfeboro Bay, where there's very limited data. We're looking for people to collect on a monthly basis the samples in a couple of locations near Springfield Point, Oakwood, in Sergeant's Pond, and then in some of the lakes where there has been plenty of monitoring in the past. We need to continue that monitoring, and so there will be opportunities for people to participate there. So you can sign up for water sampling. You can also look for storm water runoff and other sources of nutrients in land near you. And if you're interested in the identification, I mean, Jim Haney pointed out that Hillary Snook from US EPA, we're having the mobile van from US EPA and folks from UNH here on June 26th. In the morning, and it'll be from 9:30 to 11. But if we end up with more than 50 people signed up, we'll end up having split sessions. It'll be at the Brewster Academy Boathouse, and so there'll be an opportunity to talk to experts, to see different types of cyanobacteria, know how to recognize blooms. And then we will talk about the protocol, as if you think you see one, what do you do? So, that's basically the local scene, and what I'd like to do now is introduce Bob Craycraft, who has. I don't even know how many years, Bob, you've been doing this, but certainly all the years that I've been, is the lead guy for UNH's extension program for volunteer water monitoring, water sampling, and he's the person who ends up providing us with the training, on how to sample. He's the one who provides us with the supplies. He's the one to whom we hand the bottles, and he's the one from whom we get the results. So a very key person, but giving results that really give us a lot of insights as to where we stand and how to devote limited resources and efforts in doing the maximum to maintain and enhance the water quality of our lakes. Thank you.
All right. Thank you, Warren, for introducing me. And I have been involved with the monitoring up here since 1988, back when I was a student at UNH. So it's been some time, and then I took on the responsibility of coordinating the program more recently. So I've been up here quite a bit over the years. My intent was to take a step back and give you kind of a big picture overview, since we're dealing with multiple lakes, some of which I work directly with, others work with the state of New Hampshire more directly. The best approach, I think, is to talk more generally, and then I can answer more specific questions if there are any. The good news is you have a lot of the water quality monitoring going on. It's taken place over the years among the various lakes in the town. Back in 1984, Wentworth and Crescent Lake came online. In the later 80s, you had Russ Pond come online. In 1991, Mirror Lake with water quality monitoring using volunteer monitors, which is really critical. One of the problems we run into as professionals, whether at the university or state or private consultant, is there really aren't a lot of data out there to tell us what happened historically. And in terms of historical documents that are published, I only know of a few that date back to the 30s through 50s, and one of them being Fish and Game. They did some surveys, and it was really for fishery habitat, what type of stocking practices they were interested in among the lakes. So those are some of the early data we have to rely on, actual physical published data. Then in the mid-70s, the state of New Hampshire began doing lake and pond surveys, but because of their limited resources, so many water bodies throughout the state, they couldn't get out there frequently. So the state has gotten out maybe every 10 to 20 years to the various lakes, and these are snapshot samplings. They're great surveys, but things can vary tremendously over time. So more recently, the groups have gotten involved with the water quality monitoring using volunteers, which is critical because things change tremendously from day to day, from week to week. So if you're not out there to catch these problems, they can easily be missed. So just using the example of the cyanobacteria, those blooms can come in very rapidly. So 1 week they can be there as indicated at the preliminary presentation, the next week they can be gone, or even certain time of day. They come from the deep water layer up to the surface and then go back down. So you have that problem. You have a spatial problem in the lake where wind might be blowing them to one end or another. So it's really critical to have eyes and ears on these lakes in terms of volunteer monitors who not only collect the physical data, but also can relay their findings, just visual findings, to the state or university or whomever you're working with locally to mitigate those problems or at least identify potential solutions to dealing with them. So really that critical, that frequent sampling is really critical. Being out there on the lakes is critical. Long-term monitoring is really important too from various standpoints, but certainly to understand long-term trends, it's really important. But going back to the preliminary discussion of temperature changes, the climate fluctuations, as things get warmer, things can grow better. The blooms can increase potentially in frequency, and we actually do see that on a short-term basis. From year to year, if we have a really warm year, Oftentimes, we'll see poorer conditions than a less warm, a cooler year. Also, rainfall fluctuations have a tremendous impact on the water quality from year to year, week to week. Wetter years, we tend to see poorer water quality, generally speaking, than drier years. And some lakes are exceptions, but generally speaking, it does come down to that rainfall really having an impact. And if you go back to the overarching issue you've dealt with the last couple of years of stormwater management, infiltrating the rainwater before that water gets into the lake, that's really critical. It goes hand in hand with the rainfall. You know, if you can infiltrate that rainfall before it reaches the lake, it'll really help purify, take out the physical particles, also help pull out some of the dissolved nutrients, which is going to be really critical for improving your water quality. I wasn't sure how far. I only had a limited time, so I was using this just to give you a very basic overview. I guess the other critical thing is with the cyanobacteria. That's a more recent component to our water quality monitoring program, and the state's doing it. The university's doing it. So it's certainly something I'd encourage everybody to get involved with. What we're doing with Winter Harbor in particular right now is expanding in Winnipesaukee, is expanding the monitoring program to collect water samples for analysis in a laboratory. So still being the eyes and ears is really critical out there. As Warren showed you with one of his images, the Gliotrichia bloom, that was very, very prevalent in certain parts of Winnipesaukee. So seeing that was really critical to getting in touch with the state and having some assistance associated with whether or not there should be closures suggested for public safety purposes. But getting these samples involves collecting water samples and sending them in for analysis. And the disadvantage is you don't get immediate results, but it does begin to track the long-term trends to better understand what's going on, whether you're reaching thresholds that are really critical in terms of trying to deal with various problems that are going on. Tracking whether there's spatial variations throughout the lake. Some areas are more prone to problems than others. So really having the hard physical data to understand whether or not there's problems is really critical, and getting involved with these types of sampling approaches is a way to deal with that. Nope.
I'm not as tall as Warren. Okay, so we're going to do this kind of like a lightning round here because we don't have a ton of time, and I tried to group these in groups that sort of made sense to me, but hopefully it'll make sense to everybody else. So this first set is kind of for Jim. And so what's the effect of boiling water on cyanobacteria? Can one wash dishes using boiled water if cyanobacteria is present? Are there treatment methods such as ultraviolet light? Does that provide any protection or filtering?
Okay, this is really an important question, because the idea of boiling water to purify it has been around for a long time, obviously. Certainly when I was a camper before I knew about cyanobacteria, that would be the first thing I would do, is boil the water. If I happened to collect water when I was camping and it was grungy looking, you boiled it, right? One of the interesting things is in our laboratory, one of the options we have for extracting the toxins from the cyanobacteria so we can then detect them is you boil them, because it doesn't break down the toxins, but it releases them into the water. So when you realize that, this is true for the microcystins and the BMAA that we have. These are generally very tiny molecules, so they're not broken down the way a whole organism is by boiling. And so first of all, the boiling doesn't protect you at all. In fact, it could make it worse. So you basically have to avoid water that looks like it may be contaminated with cyanobacteria. Now, if you wanted to go to drinking water, which is, we've been working with drinking water sources and with DES on that a bit. We're hoping that within the next year we'll be offering a certificate perhaps for people doing drinking water and others to simply educate on how do you sample them, how do you measure them, and that sort of thing. But there are treatment forms that can be used by drinking water, for example. You can raise the level, depending upon the toxin that's present, you can raise the level of disinfectant to a point where, in fact, it will destroy the toxins. It's unfortunately higher than we normally use for drinking water, so that you have to consider that. Also, ultraviolet light can. But if we talk to the Manchester Water Works, for example, and they process such a large amount of water that to get the level up to where they could remove the toxins would be an expensive operation. So there are practical reasons why this is not always possible. So obviously, if you have a choice, the best thing is reduce the levels of toxins so you don't have to destroy them.
Okay, just a quick follow-on. Is it possible for cyanobacteria to be present in groundwater?
That's that's a question we're going to approach down at the Cape this year, because with the help of the U.S. Geological Service, who's been working on groundwater down in that region, and the Cape is a special example because it's largely a sand-based soils. And so sand, as you can imagine, percolates the water very easily. Some studies have been done in the south to show that actually if you're near a lake, within about a mile of a lake in a sand area, that high levels of the liver toxins, microcystins, can flow into the groundwater. My knowledge of the geology here is limited, but it certainly suggests there's we use rock fissures, for example, which can transmit very quickly but very locally. So it's hard to generalize, and we don't have enough information to say how much the groundwater is, if it is contaminated.
Okay, I'm going to have Bob take this next one, since he's on the front lines of a lot of the monitoring stuff. How do researchers and citizens stay safe when they're collecting cyanobacteria data from both aerosols in contact with the water?
Well, I mean, when you're out there, you don't know what you're dealing with. So if you see certainly if you see a true scum, ideally you'd have some type of protective gloves on. People, I mean, you saw one of the images up on the Dr. Haney's presentation at the beginning that showed a researcher collecting it without any protective gear. And we kind of joke at the university about that. We should have full hazmat suits, and maybe we should, but we oftentimes don't. But realistically, to be safe, it's better safe than sorry. So I would suggest having the gloves on if there's any chance of being exposed.
I'd just like to add, in defense of Hans Perl, whose picture I showed, when I told him I use that picture sometimes, I saw him at a meeting, and he said, I regret having had that picture taken.
Okay, the next question, are blooms more prevalent in shallow areas, and what might be the effect of drawdown, seasonal drawdown on blooms?
You want me to take that?
Sure.
Okay, sure. Well, they're more obvious in shallow areas, and one of the things about shallow areas is, I mentioned to you, the idea that these blooms can form by essentially collecting from the rest of the lake is really important, because we don't often know how much is generated in the shallow water. I will say, however, that humans like to take responsibility for most things in the world, even if they're not responsible for them. One of them is lakes take a certain responsibility for blooms. If a lake is designed in a certain way, it's a perfect culture chamber for cyanobacteria, even without any interference by people. There are naturally blooming lakes. And one of the requirements is that they're shallow, so that light reaches the bottom, so they've got contact with sediments. Even if there's very little nutrients in the water, the sediments have the nutrients. And one example of that is Silver Lake in Hollis, which we've studied quite a lot. There's a beach there. And that lake has been blooming for the last 30 years since I started studying cyanobacteria. And it has not a heavy level of phosphorus coming in, but it uses what's on the bottom. So it's a natural chamber. So shallow lakes can be a problem, especially if it's oligotrophic, because that's where the phosphorus is, and that's where the cyanobacteria go.
Okay.
Maybe I can ask my colleague. In reading the reports about gliotrichia, it seems to be, it doesn't seem to follow all the same rules as some of the other cyanobacteria, and seems to be particularly associated with shallow water. The studies in Lake Sunapee, for example, seem to indicate that the gliotrichia was coming up from 15 feet deep or less.
That's very true. I think gliotrichia is the exception to the rule that cyanobacteria like turbidity. And the reason, as I mentioned, is that they generally can use low light levels, so that when it's turbid, that excludes a lot of other types of phytoplankton. But gliotrichia, it is designed as sort of a sponge. It goes down in the sediments, soaks up the nutrients, and it's big enough it can hold on to them. And then it comes up, and it's good. It's like, if you're going camping, you pack up your backpack. It's got a backpack full of phosphorus, and it can multiply several times just based on that internal phosphorus then. So its ideal thing is a clear lake that has phosphorus in the sediments, which most lakes do. And we did a survey, along with some other researchers, of the lakes in Maine and some in New Hampshire, looking at the occurrence of toxic gliotrichia. And it turns out that some of the clearest lakes have these populations of gliotrichia. So the trick there is to starve them if you can. That is, reduce that phosphorus load in the sediments. And the sediments, they're constantly being overridden. It's like my desk at school. It's constantly there's a sedimentation rate, and the things on the top are what I see. And for those cyanobacteria, it's the recent sediments that make a big difference in a lot of those. So if you can stop putting phosphorus in, it essentially gets overlain with a layer of low phosphorus. So that's the hope.
Okay, I'm going to do 2 more questions before the break here, and then we'll pick up the rest maybe after the break, since all that nice food is out there, and I hate to see it go to waste. So is there any natural enemy at any stage to the cyanobacteria? Is there in other words, is there a stage where it's vulnerable to be eaten by something else? And can we control it that way?
One of the ideas is, and people rightly so, and we always ask the same questions: why are they producing these toxins? Why are there so much toxins associated with them? It takes energy to do that, and nature would tell you that you don't do things without a reason when it comes to using your energy. It's allocation of resources. We do that every day. Do I go on a vacation, or do I pay my taxes? Whatever. So very difficult decisions. And the idea is that these toxins cost something. So what's the benefit? And one of the benefits is that they can help with the competition with other phytoplankton, but also they help, so other phytoplankton can be an enemy of the cyanobacteria if you can promote them. One idea is you can dump silica into a lake to prevent then cyanobacteria, because it promotes diatoms. And so the diatom population competes for the phosphorus. So you can play that game. The other is that these toxins are preventing certain zooplankton from eating them. And that's the other side to it. These Daphnia that I showed you, they won't eat big things, but they also won't eat the small cyanobacteria if they're toxic. So that's the answer is there are organisms that do eat them, and we can try to promote those. And that's where you have to have a balanced ecosystem. We're working with Norway Pond right now because we did a toxin study there, and one very similar to what we're hoping to do here in Wolfeboro next fall with my class. And one of the things we discovered is that the Daphnia had eaten lots of cyanobacteria. They were full of these toxins, but they weren't going into the fish. And that's an interesting question. Why didn't they go into the fish? So we're just learning about this whole thing of what eats them and how does that affect their movement. But I think we will be able to control somewhat by modifying the food web.
Okay. And here's the last one, and I think maybe it'll be a quick answer. Do you have to ingest cyanobacteria through the mouth or nose, or can it be absorbed in other ways?
Well, this is a big question because of our concern with aerosols. You know, the aerosol story, the thing that I didn't mention, to go back to oikos, which is the house, the ecology meaning house. You know, as we think about being self-serving whenever we take care of our lakes, because there are lakes, right? But if you think about the study that showed that an area, a perimeter of 30 kilometers around a lake represents an area where statistically people could be affected by water quality, that means Lake Winnipesaukee is not, and Wolfeboro Bay area is not a responsibility of you, but it's responsibility of everyone in this area. And one of the reasons is that aerosols then could be carrying toxins that people are breathing, so that you can't avoid the effects of a lake. It's a community responsibility. Wentworth or whatever, Crescent, these are all part of affecting people at the other end of the lake. The other end of the lake, and Winnipesaukee is a great example of they describe it as having, 365 islands, so one for every day of the year, but actually it has almost as many lakes in it. And the thing that's interesting about Winnipesaukee to a limnologist is that each one of these then is influencing other parts of the lake, both by aerosols and interacting. So if you go up in the Tuftonboro area, those are very different lakes than Alton Bay, for example. So, but they're all interconnected both by water and by air. So when we work on these, I think if you can convince the community that this is as important as air quality from other sources, I think that connection's important.
Yep, and how about skin exposure?
And so lung exposure, they claim, is about 10 times more effective in transmitting the toxins than ingesting. So if you were swimming or eating something. Skin exposure, many of these cyanobacteria produce toxins that causes rash on skin. That causes rash on skin. So these are not as serious, perhaps, as some of the chronic exposures, but they do cause rashes and such. And many of these have been reported even in New Hampshire of people having rashes from swimming.
Okay.
Yeah.
Okay, so I think we'll take a quick break now. Don't go far. Well, we have more questions to come, and then we've got another panel with our local lake representatives coming up.